Hi, and welcome to 12 IPT, Option 4, Multimedia Systems, Topic 1, Characteristics of Multimedia Systems. Today is Activity 3, Demands Placed on Hardware. Please pause if you'd like to read the dot points that this activity covers. So, multimedia places a high demand on hardware. In terms of syllabus, you're required to be aware of the demands that placed on hardware in terms of primary and secondary storage, processing, and display devices. First, we need to define primary and secondary storage. So in computing, primary storage refers to the storage that is the most important to the computer, which is RAM, ROM, cache, and registers. This is not a hard drive, even though we consider the hard drive to probably be the most important storage for us. To a computer, it's actually RAM, ROM, cache, and registers. So, RAM stands for random access memory, which is a large storage area used to store information taken from the hard drive ready for future processing. It is much quicker to access than a hard drive. It's volatile memory, meaning that it is cleared when your computer is turned off. Um, we have ROM, which stands for read-only memory, which is a small storage area used to store information required by the computer that will not change. Typically, system settings and important booting information. It is non-volatile memory, which means the contents are stored even when the power is turned off. So RAM, temporary, turn your computer off, it wipes the memory. ROM is permanent. Okay, it's stored when the power is turned off. Cache and registers are small storage areas used similar to RAM. They are extremely quick to access, making them useful for information due to be processed. So these sit right next to the processor, and they allow the processor to store small bits of information to process really quickly. And here's a diagram of the different storage. So we can see that information goes to and from the processor from the cache and the registers, and then that calls information and sends information to RAM, and then that will send information to secondary storage and call it up to RAM as well. ROM, obviously, read-only memory. It only gets read from to cache and registers, which will then move around the processor and back to cache. Secondary storage refers to storage that is not as important as primary storage, generally bulk storage, such as hard disk drives, which are massive storage devices used as the main storage information. They're non-volatile, which means they keep their memory when you turn them off, and it uses electromagnetism, so hard disk drives are magnetic disks. Solid state drives, or SSDs, they're storage devices used as an alternative to HDDs or hard disk drives. They're also non-volatile, and they use circuits, or what we call flash memory, to store information. We also have a hybrid drive, which is a combination of the two. Solid state portion is small, which holds frequently needed information, such as the operating system, and we also have a large hard disk portion to store other data. And it's a compromise between speed and cost. So solid state drives are extremely fast, but also extremely expensive. Hard disk drives are cheap and not as fast as SSDs. So with a hybrid drive, you have the small, fast bit, so it's not as expensive to put on, but only the most frequently accessed information, such as the operating system, is stored on that. Then we also have the large, cheap portion, which we use to bulk store the rest of our data. We have CDs, DVDs, and Blu-rays, which are all variations on the same disk technology. They're used as portable storage and archival storage. They're also non-volatile, and they use lasers to read and write the information to the disk. The only difference, or the main difference between each of these, is they use a different type of laser to write the disk, a smaller wavelength. As you go from compact disc to DVD to Blu-ray, the wavelength of the laser is smaller, which means it can write more information in the same size space. We also have flash memory, which is USB sticks and SD cards, etc. And they're physically small devices, but they have large storage capacity. They're very durable and very fast, which allows users to take data with them in relatively safely. We're not sure just yet as to the archival storage uses of them because they haven't been around for too long. We also have network attached storage, which is a hard drive or server attached to a computer through a network. This is useful to store large files and have them accessible to a number of computers, such as for project files for teams. And we have storage area networks, which is a network of storage devices. And they're used by a computer as separate virtual hard drives, enabling many virtual drives to be stored on one physical device. So the advantage here is that instead of having multiple hard drives, which could have various amounts of information on them, you have one server or a number of servers with a number of virtual drives on them, and depending on how full they are, you can cram lots of virtual drives onto one actual drive, saving on the number of storage devices you actually purchase. Okay, so in terms of units, we have a bit, which is the smallest unit of storage. It's either a 1 or a 0, on or off, high voltage or low voltage. That's the smallest unit of storage that we use in computing. We also have a byte, which is 8 bits, and the byte is what we generally use when we talk about storage in computing. We have multiples of bytes, which increase according to the standard SI notation. So we have K for kilobyte, M for megabyte, G for gigabyte, T for terabyte, and P for petabyte. The problem is with bytes, we have two different number schemes. Computers use the binary number system, which can only store ones and zeros, and we use the decimal system, which has values from 0 to 9. With that, all of these, they go up by 1,000. So in binary, what people know as 1,000 is actually this number here. It's not exactly 1,000, and it's not a simple number, as I've said here. And the closest number is this, which is actually 1024 in decimal numbers. So computers will sort of round it off. When we talk about kilobytes and megabytes and whatever, we're actually thinking about 1,000. But when the computers think about it, they're thinking about 1024. And so we have a discrepancy. If we have a kilobyte, we would think of that as 1,000 bytes, but the computer would think of it as 1024. And this difference is compounded the more the larger number of storage that we're looking at. And so we have this, which is we have kilobytes, which is the bytes that we use, and we have kibibytes, standing for binary byte, which is what computers use. And so you can see the differences there. We go from 1,000 to 1024. If we're looking at a megabyte, our megabyte is a million bytes, whereas a computer's is 1,048,576. And you can see that number gets bigger and the difference gets bigger as you go up through the different sizes. So you need to ensure when you're looking at storage, you're actually looking at the right number of bytes. Whether you're looking at actual kilobytes, which are these ones here, or kibibytes or whatever. Okay, so storage requirements related to color depth. Visual data such as images, video, and animation can easily take up a large amount of storage space. When storing visual data, the computer needs to store the color of each pixel in each image. The number of possible colors determines the amount of memory this takes up. So when we're looking at 8-bit color, that's 2 to the 8 colors, which is 256 colors. We're looking at 16-bit color, 2 to the 16, which is 65,000 colors. And we're looking at 32-bit color, it's 2 to the 32, which is many, many, many colors. We have other standards as well. I think you've got 24-bit color and so on. It just means that you have many more colors to represent. If you have an image saved in a certain color scheme, then for every pixel, it will store the number of bits of information. So with 8-bit color, each pixel uses 8 bits of memory, or 1 byte, to store the color of each pixel. If you have 16-bit color, the colors the colors will not change because they just get converted from 8-bit to 16-bit color. But the image will double in actual memory size because it now needs to use 16 bits, or twice as much information, to represent each color. When looking at audio file sizes, we need to look at sampling rate. So when a sound is recorded, the whole recording is not saved. A computer can only record snapshots in time, or samples. So the more samples per second, the closer the recording will resemble the original sound. The number of samples are measured in hertz, and some common sample rates include 11.025 kilohertz, which is 11,025 samples per second, which is a low quality audio, and that goes up to 44.1, which is audio CD quality, and we have many higher sampling rates as well. So obviously the more samples per second, the higher the sampling rate, the more data the computer needs to store. So if you're looking to save space, you need to use a smaller sampling rate, and if you're looking to get the best quality, you'll use a higher sampling rate. Processing requirements related to frame rates. So video can be a very processor intensive process. One aspect that affects the processing required of video is the frame rate. A frame is a still picture from a video. To get the illusion of movement, the frames are shown at a set speed, and the frame rate is the number of frames displayed per second. The more frames, the smoother and more lifelike the video. Frame rate is measured in FPS, or frames per second, and the more frames there are, the more data in the video, and therefore the more data that needs to be processed when rendering or viewing, and also the more data that needs to be stored when saving your video. So processing requirements related to images. Image editing also can rely heavily on the processor. As the image size gets bigger, obviously the computer has more work to do to render the image. Using tools to edit the image may also require lots of processor time. Two operations which can be processor intensive include morphing, which involves a change from one picture to another, and distortion, which changes the image by changing the angles or length of the side of an image. So the creation of animation can also be a processor intensive process. One of the key features of computer-based animation is tweening, where the user creates the first and last frame of an animation sequence and the computer will fill all the frames in between. When playing this animation back, the computer needs to do extra processing to create the frames needed. By increasing the amount of tweening, you increase the amount of processing the computer needs to do, but you reduce the file size. If your animation lags as it plays, one solution could be to reduce the amount of tweening in your animation. Pixels and resolution. The increase of quality in multimedia has also affected the demands placed on display devices. So display devices have physically become larger, both in terms of desktop computer screens and TVs. You can see that with just how large TVs are now compared to even 5 years ago. They're quite large now and they're getting bigger all the time. With that, the resolution of these screens has also increased to make sure we maintain a clear picture, as well as the refresh rates on the TV as well. And these screens need to have much more powerful hardware than they used to be able to handle the massive amount of data they are required to. So an example here, we've got 480i resolution, which is your original standard resolution for a TV. 480i is 640 by 480 pixels, which is 307,200 pixels for each frame displayed on that TV. We go to the newest standard at the moment, which is 4K, which is a resolution of 3,840 pixels by 2,160, which is 8,294,400 pixels. So that equates to 27 times the data of a standard TV for every frame displayed. So that's just an indication of how much data these TVs are processing every time you turn them on.